This video is going to be on light and the electromagnetic spectrum. Now, what we refer to as light, like when you turn on a lamp and you see light, that's only a small portion of an entire electromagnetic spectrum. Some that we can perceive, like the visible lights part of the spectrum, and some of it we cannot perceive with our eyes, but is still around us all the time anyway. This is a diagram of the electromagnetic spectrum showing you from the longest wavelength with the lowest frequency all the way up to the highest frequency, shortest wavelength waves. And the division between the two, or between all of the different types of waves, is just based on the wavelength. Light travels at a set speed, the speed of light. And when I say light from here on out, I'm talking about electromagnetic radiation, not just the visible light that we see, but all of the electromagnetic radiation. So radio waves, microwaves, infrared rays, visible, ultraviolet X-rays, gamma rays, they all travel at the same speed. So the difference between them is the wavelength. And of course, when you change the wavelength, as a result, you change the frequency of the wave. And the frequency of the wave is what will give it its different properties, different abilities to cause cancer or be able to help you see or send communications back and forth. That's all dependent upon the wavelength and the frequency of that wave. So we're going to kind of take a tour of the spectrum. We'll start off with the longest wavelength, the lowest frequency, and that would be radio waves. Now, yes, it is the type of radio that you listen to when you're driving in your car. Yes, radio. Radio waves can travel through obstacles. The waves themselves, of course, remember this is moving energy. They're too low wavelength and the frequency is too slow for the atoms in walls to deflect them. So even when you're in your house with the door shut, you could still hear the radio. Radio waves are typically used for communications, not just the radio, like music radio that you think of, but also things like the transmitters between ships out to sea and some satellite communications on the radio wavelength frequency. So it's used for sending information back and forth from one place to another. Microwaves are also used for communication. They're just a little bit smaller than radio waves. Their wavelength is only a few centimeters wide. They can also be used for cooking food. When we did the popcorn lab and we made popcorn, we talked about the microwave oven and how it emits microwave waves, microwave radiation. These wavelengths that are only just a few centimeters or even smaller across are just the right size to grab those water molecules and for the water molecules to absorb them and increase their energy. Remember, and then thermal energy, it makes it hot. So your microwave oven will emit microwave radiation that will be absorbed by the water in your food, which will then give it energy to move around and be heat, be thermal energy. But microwaves don't necessarily have to do that. You can go to a little bit bigger wavelength and get the type of communications that our cell phones use and that satellites, like your satellite TV, that they use. That's all microwave radiation as well. Shorter than that is infrared rays. Infrared rays are just slightly longer than the visible spectrum, which is right there in the middle. The infrared radiation we absorb with our skin. Remember, microwave can be absorbed by water. Infrared can be absorbed by our skin, which we feel as heat. So when you're standing next to, say, a fireplace and you feel the heat that's radiating off of the fire that's burning in the fireplace, that you're absorbing infrared radiation and your skin is perceiving that as heat energy. But some animals can actually see infrared rays. Their eyes are adjusted to see, like think snakes, pit vipers. Snakes have these pits, these heat-seeking pits in their skeleton, in the front of their face that will take in infrared rays and interpret those infrared rays just like we interpret visible light with our eyes. So they can see in infrared. The image below is a picture in infrared, and we can see the different temperatures of this guy based on the infrared radiation that he's given off. So night vision goggles, heat-seeking cameras, those are all using that infrared spectrum of light. The visible spectrum, that's what you're most familiar with because this is the spectrum that your eyes can pull in and interpret. It contains all the wavelengths that we can detect from the longest, which is red, down to the shortest, which is violet. And there's a little way to remember it. It's called Roy G. Biv. Roy, R-O-W, red, orange, yellow, G in the middle, green, and then B and V, blue and violet. And that'll help you kind of remember how to put them in rainbow order, so to speak. Ultraviolet radiation is just slightly higher frequency than the visible light, than the violet color. So you have the violet color that we can perceive, and then you have ultraviolet. Think black lights. Black lights give off ultraviolet radiation, and then you can even get beyond that into wavelengths that we can't perceive at all, beyond black lights. But some animals can see in ultraviolet. Butterflies and birds can see in ultraviolet, some species, and that helps them find different types of flowers. Different types of flowers will give off different colors. They will fluoresce. Certain animals even will glow under a black light, will fluoresce under ultraviolet radiation. Now, ultraviolet is slightly higher wavelength, or sorry, shorter wavelength, higher frequency than visible light, and it can cause cancer. It can be small enough to disrupt the cells that are in our bodies. And so one way that our body tries to combat that or try to prevent that is by putting up a dark barrier in the upper layer of our skin, which is a suntan. So when you get a suntan, what your body is doing is trying to put out pigmentation, that dark color, to block that ultraviolet radiation from getting deeper into your skin. So that's ultraviolet. You definitely want to be careful and use suntan lotion with ultraviolet radiation around. X-rays, a little bit higher frequency, shorter wavelength. These will actually go right through soft tissue, but they still will not penetrate hard tissue. So they make really great images for bones, as well as other industrial uses. It'll go through things that are soft, but it will be stopped by things that are dense. So you see the little x-ray down here. Some of you have gotten x-rays before. You can see the hard tissue because the soft tissue lets that ray go straight through. Gamma radiation is the highest frequency, the shortest wavelength, that has the most energy to it. It can penetrate our cells and it can actually destroy our cells. If you hear of someone getting radiation poisoning, that's usually gamma radiation. But the same rays that can cause damage can also help. We can use that power to kill cells and use gamma radiation to kill cancerous cells. So you see the little man on the table down here with, he's got a tumor of some kind. You've got gamma rays that are focused on the tumor that will penetrate that tissue and kill those cancerous cells, hopefully leaving as much of the healthy tissue in good shape as possible. So that's becoming a really interesting medical technology, is using the gamma radiation not just for harm, but for good. And it'll also kill bacteria. A lot of sterilization processes will use radiation to kill the bacteria that's on surgical equipment, needles, things like that. They'll help sterilize the medical equipment. So that's a tour of the electromagnetic spectrum, from the longest radio waves all the way through, of course you see visible light right there in the middle, all the way through the X-ray radiation. And now let's kind of look at what light does. Now, when we think of white light, the light when you flip on a light switch, all of that light is the entire spectrum coming to you at one time. So when you combine all the colors, when you're getting all of the energy coming to you at once, either from the sun or from a light bulb, you see that as white light. We see two pictures down here of prisms, and prisms we'll talk about more when we talk about refraction and dispersion, but for now we'll just look at the prism as you have white light coming in, and then the bending of that ray will separate your white light into its different colors. So you'll see from red all the way to violet, and that's how we get rainbows. When you perceive colors, not white, but when you see green or when you see blue or orange or yellow or whatever, what you're seeing is the light that is reflected back at you. So if I'm looking at something that is green, that object is absorbing the other colors of the spectrum, of the visible spectrum, and bouncing that green wave to me. So I see that green wave. They have the diagram down here. If it's white, you're reflecting everything back at the person that's viewing it. If it's black, it's absorbing. So they tell you during the summer to wear light clothing and during the winter to wear dark clothing. The light clothing will bounce that sunlight off. It will reflect the sunlight, and along with sunlight, you have infrared radiation, so it'll bounce that heat off and keep you a little cooler. The black will absorb all of that energy from the sun and absorb that infrared radiation and make you warmer. So during the summer, wear light reflective colors. Polarization is kind of a neat one. Polarization kind of stumped me for a long time, but here's how I think about it. You've got two different directions of vibration with electromagnetic radiation. You've got two fields that are vibrating perpendicular to each other as the wave travels. And so when you hit a polarizing filter, it takes out half of that vibration. It's kind of like you've got this big wave that's vibrating through space, and then you hit this slat, like this picket fence. And only the wave that's vibrating with the slats of the picket fence can get through. So there's a picture down there of a filter that's filtering out the horizontal radiation, or the horizontal wave. Then there's one that's filtering out the vertical wave. And then there's one, of course, if you turn them both on, you don't get anything. Polarization is useful. You might have heard of polarizing sunglasses, polarizing lenses. There are sunglasses that they make, especially great for fishing. When you're on a boat and you're fishing, you get a bunch of glare off of the surface of the lake, but those polarizing filters will cut that glare down. You're only getting half the wavelength of light, and so you don't get as much light coming into your eyes, and you can see better with that polarizing filter. It'll cut down on the glare. The bottom right picture is a polarizing filter on a camera. This is a kind of a misty field out there on the morning, and so that mist and the morning sun is making a big glare that would be really hard to capture with a camera, but with that polarizing filter you reduce that glare and you get a much clearer picture of that dewy meadow. This is where I used polarizing filters. When we were studying rock samples in geology, a lot of times you would look at the picture on the left and you'd be like, okay, great, it's a rock. But once you looked at a thin section, a thinly cut section of a rock under polarized light, it would cut out half of the wavelength that's coming to you, and you could see the different wavelengths, the different colors coming at you, and that's one way that you can identify the different materials that are in rocks and minerals, is based on their properties under polarizing light. So that's where we're ending today. When I come back tomorrow, we will talk about this light and electromagnetic spectrum, and then we'll move on to how waves behave. So I hope you have a great day. Don't forget to take your quiz when you're done.